Welcome to this talk in the context of SAM conference to be held in Las Vegas in July 2020. My name is Raúl Durán and I speak on behalf of my co-authors Luis Hernández-Álvarez, Luis Encinas, Araceli, Queiruga. The title of my talk for today is Chor-Rivest Knapsack Cryptosystem in a post-quantum world. Briefly, in this talk, we want to show that knapsack-type cryptosystems may very well deserve a proper place among quantum-resistant proposals. Let's review a little bit the contents of the presentation. First of all, of course, an introduction to the topic. Then we will very briefly review the proposals for post-quantum world. Then we will enter into the Chor-Rivest knapsack cryptosystem. That will be the core of our presentation. And finally, some discussion and future work. Let's remind and let's recall some very well-known facts, like, for instance, the now famous Shor algorithm that dates back to 1997 that is able to break integer factorization problem and also the discrete logarithm problem in polynomial time. This is a very nice piece of news, since almost current worldwide deployed asymmetric cryptosystems are based upon these two problems, upon IFP and TLP. That means that with the advent of a possible quantum computer, all this type of cryptosystem would be broken. It's no surprise then that the NIST has launched an international call for proposals of quantum-resistant cryptographic algorithms for any type of cryptography, both for asymmetric, encryption or decryption, digital signatures, key encapsulated mechanisms, and everything, with the objective, of course, of selecting the best cryptographic primitives that are invulnerable, at least as much as we can, to quantum computers. That's what we call quantum-resistant algorithms, no matter how much computing power they can have. To the date, the most important candidates submitted to NIST has been categorized as those that we can see in this slide. We will review very soon each of these categories. Let's go now to our proposal, which is the knapsack problem, which consists in the following. Given a finite set of positive numbers, A, with numbers A1 to AN, that's what we call the knapsack, and given a positive integer S, the problem is to determine a subset of A, such that its elements, the elements of this subset, add up to exactly S. Now, a cryptosystem using this knapsack problem consists of a subset S of the set A and a transformation that depends on a secret key, such that the problem is easy before the transformation and is hard after it. The good piece of news is that knapsack problem has stayed safe in the face of quantum computing. In particular, we will review Chor-Rivest cryptosystem, which is interesting and rather involved. Let's review now the categories of these post-quantum proposals. First of all, we have hash-based cryptography. This proposal essentially provides a quantum-resistant signature scheme where the public-private key pair can be used safely only once. That's why this is called a one-time signature. The key ingredient is a pre-image resistant hash function H. And the good piece of news with this type of cryptography is that this signature scheme remains safe as long as the underlying hash function remains hard to invert, even in the presence of quantum algorithms. Code-based cryptography is based on the idea of correcting codes for electronic transmissions over noisy channel. The correcting code adds some extra information to the transmitted information, allowing the receiver to reconstruct the original data, even in the presence of transmission errors, by using the same correcting code, both in the sender and in the receiver. The sender adds noise to the transmitter signal. That's the message. In this way, he is able to hide the information. This noise can be filtered out by the receiver, provided he has got the right correcting code matrix, which plays the role of a secret key. Now, lattice-based cryptography is basically formed by two very popular problems, learning with errors problem and ring learning with errors problem. They are rather complicated, but let's review it very fast. Given parameters n and q, we choose a secret vector S of integer numbers in set Q, and we form pairs by selecting random vectors, also integer vectors, and we multiply each AI times S via the inner product. And then the problem is to find, in principle, the problem is to find the second vector S. This is simply a linear set of equations that could be solved very easily using simple Gaussian elimination, for instance. But what we do now is to add some noise here so that the problem becomes very difficult. That's the search version, find the second vector S, and also there is a decision version in which, in given pairs A and B, we must decide whether they have been generated as above or they are truly random. The second flavor of this problem is the so-called ring learning with errors problem, which is analogous to this LWE scheme, but using elements in a different set, the so-called ring RQ. Last, we consider the MQ problem, multivariate quadratic equations cryptography. The MQ problem over a finite field of Q elements of Q consists in finding a solution X to a given system of M quadratic polynomial equations P over FQ in n indeterminates. Its polynomial is simply a quadratic polynomial with quadratic terms, linear terms, and independent terms. It's known that this problem is NP complete over any finite field when we randomly select polynomial vector P. Using this problem and endowing it with some structure, we can define encryption and decryption and signature schemes. Now, after reviewing these post-quantum proposals, we turn to our core of our presentation, which is the Chor-Rivest Knapsack cryptosystem. Chor-Rivest cryptosystem is based on the Knapsack problem that we saw before, and it works with arithmetic in finite fields. The interesting point for this cryptosystem is that it needs to compute discrete logarithms in order to determine the keys of the system. That means that the easier the discrete logarithm computation, the better for this cryptosystem setup. This means that if we are if we have a quantum computer, and by using the Shor algorithm, we will be able to compute these discrete logarithms very fast. So that's much better for the cryptosystem setup. Another good piece of news is that Chor-Rivest Knapsack has always a density greater than 1. So all low density based attacks are not applicable. It's known that Chor-Rivest cryptosystem, which it's really old, dates back to 1988, was broken very soon for specific parameters. Those attacks enable the recovery of the private key from the public one. But remember, back to 1988, it was very hard to compute really good keys, since we needed to compute these discrete logarithms. So today we know, and we have performed some research in this direction. We know that they do exist some parameters that are not vulnerable and not attackable with these algorithms. Knapsack problem is considered a decision NP complete problem. Let's review a little bit how it works. First, key generation. Key generation is performed in the following way. First of all, we need to select some parameters. We will work in a finite field, which is an h-degree extension of a ground field FQ. We always use finite fields. We need an irreducible monic polynomial of the h that we call f of x with a coefficient in fq, and we need a generator of the multiplicative group f star. And using this generator, we compute algorithms for all the elements in the ground field fq. These logarithms here are computed and stored as these values ai, so that using this index a, each element in alpha a in fq has its corresponding logarithm ai. But now we use some permutation pi, which completely changes the order of these indexes. And so we generate these values b by reordering the values a with this permutation pi, and then we add some noise. We consider a randomly chosen integer number r, and we sum this r to all the b's, so that we get finally these values ci. Its ci corresponds to the bi by summing the noise r, so that the public key is eventually the set C0ZQ-1 that will play the role of the knapsack, and also the parameters q and h that define the system. And we will see how a user can simply encrypt a message, and the receiver, using the private key, we will see that he will be able to decrypt the ciphertext received by using the set T, which is a root of this irreducible monic polynomial defining FQH, G, the generator, pi, the permutation, and R, which is the noise. Let's review the encryption process. It's very simple. It just consists of first converting M, the message, into a vector of q bits with weight h. That means that it has exactly h bits set to 1. And so this vector here, this vector is a vector of bits, only h bits are 1. So what we do to cipher M is simply to sum all the C elements such that its index corresponds to the index of a 1 in this vector of the message. Of course, modulus q to the h minus 1, which is the order of the multiplicative group f star qh. Now, the decryption process can be carried out by the legitimate receiver, and he receives the ciphertext C, and the first thing he must do is to subtract the noise R, thus obtaining C prime here. And of course, he's able to do so because he knows the private key. And then, using some algebra, a little bit involved, one can see that G raised to the C prime gives eventually a polynomial in X, so that the roots of this polynomial are exactly those elements in FQ such that correspond to the indices after permutation that were 1 in the original message. In other words, by computing the roots, by simply evaluating the polynomial for any of and all of the elements in FQ, we can decrypt very easily the ciphertext C to recover the message M. Let's consider now the attacks against Chor-Rivest Cryptosystem. The known attacks actually only succeed for the parameters originally proposed by the authors that were essentially very low, because, as I said before, the system was proposed in 1988, so the values for the parameters were really low, like the ones you may see here, so that the order of FQH star, of the finite field and where we are working, the order was rather low. Let's say that this N, which is the order, has 56, 50, 58 or 60 digital numbers, decimal numbers. This means that if this number is small enough, then certain attacks, like the one by Snorr and Hernández, or other ones, both specialized and also general, may succeed. But if one is able to raise those values, maybe the system becomes safer. Yes, that's true, but Vodene in 2001 discovered an attack that worked also for greater values for a much broader range of parameters. And this attack exploits the fact that this cryptosystem has equivalent secret keys and is able to recover one of them. An equivalent key is in general different from the original secret key, but it works in the same as it were the right one. That's why it's called equivalent. So if one is able to discover one of these secret keys, then the system is broken. And the bad news is that there are quite a bunch, a big number of these equivalent keys. However, and now we have the good piece of news, Vodene's attack is ineffectual if Q is prime and H is prime or the square of a prime. So, all the attacks described so far, which are all the known attacks, only work if the original parameters are used, which were very low, or we have used exactly the parameters for which Vodene's attack work. So we are in the position of searching for more parameters which could be invulnerable to those attacks. That's what we did, and the existing research proves that there are many pairs of parameters Q and H that verify the conditions that we have seen and thus thwarting those known attacks. In our paper we included a number of pairs verifying these conditions, and for instance we show here some of them, and for instance it's interesting to look at this last row here where Q is 1123 and H is 13. Observe that these two values are prime numbers in fact, and here we see that the key length is rather large, more or less 150 kilobits. Of course, at the 1988 this key size was very big, but not today, and especially if one considers that NIST proposals have in some cases key sizes around 1 megabyte. Observe also that the density is 8, which is really big, so we thwart really all known attacks, including Vodene's attacks. Next, we perform an experimental setup in order to see how performant was the system using these safe parameters that are in these columns here, and really to see if this system could be usable in practice. And we chose, as you can see, three message sizes, one small, one medium, and one large. And from the table one can see that really the system is performant for the small message, which is 1 kilobyte, where the encryption and decryption time are more or less one tenth of a second. So to conclude, we see that modern advances in quantum computers pose a looming threat to current cryptosystems. So we need to define post-quantum, quantum-resistant algorithms, and in this scenario we see that CRC, Chor-Rivest Cryptosystem, has not received proper attention. Its security has not been analyzed in due detail. So what we propose now is to use this cryptosystem, since it needs to compute discrete logarithms in order to set up the system. So a quantum computer would be most beneficial for it, because we could then be able to use much longer and thus safer key sizes. So as a future work, we suggest several lines. Increase the key sizes so as to be safe in the face of quantum computation, analyze the security of the cryptosystem endowed with these new parameters, and improve the generation process so as to thwart attacks based on the equivalent keys. Thank you very much for your attention.